163.5 centimeters. That is how much the ground beneath Pozzuoli, Italy, has risen since 2005, measured at a fixed monitoring station, recorded weekly, published by the Italian Department of Civil Protection. Not estimated, not modeled, measured. 3 million people live inside or directly adjacent to this system. The ground is still moving, and the last 2 times it moved at this scale, tens of thousands of people were forced to leave. This episode answers 4 questions. What is the geological record showing about CAMPI FLEGREI right now? In data, not in headlines? Why has the ground already been evacuated twice in living memory, only to be reoccupied both times? What does the longer physical record, written in stone, ash, and sediment, say about how this system actually behaves? And what is the gap between what the science can measure and what it can promise? By the end of this video, the record will be clear, not a prediction. A reading of what the ground has already written, and what it continues to write every single week. Buried Earth covers the geological record that standard reporting leaves unread. The technical term is bradyseism. It derives from the Greek brades, slow, and seismos, movement. The word sounds academic. The phenomenon is not. Beneath the CAMPI FLEGREI caldera, a volcanic depression roughly 12 kilometers wide by 15 kilometers long, sitting partly submerged in the Bay of Pozzuoli just west of Naples, a combination of magmatic gases, hydrothermal fluids, and accumulated heat presses upward against the underside of the crust. The crust responds the only way crust can respond under sustained pressure. It moves. Since 2005, the movement at the Rione Terra monitoring station in Pozzuoli has been consistently in one direction, up. By March 2026, the cumulative uplift had reached 163.5 centimeters. That figure comes directly from the Italian Department of Civil Protection and the INGV, the National Institute of Geophysics and Volcanology, published in their official monthly bulletins. The measurement covers approximately 7,600 days. Run the arithmetic. The ground beneath one of the most densely populated coastal zones in Europe has risen an average of more than 2 millimeters per week, every week, for over 20 years. That number requires comparison to mean anything. In 1970, the ground beneath Pozzuoli began rising rapidly. Over roughly 2 years, the cumulative uplift reached 177 centimeters. The rate was fast enough, and the resulting seismicity intense enough, that Italian authorities ordered the evacuation of the Rione Terra district in March of that year. Hundreds of families were removed from the ancient stone promontory above the bay. Most never returned. The district stood partially abandoned for decades. In 1982, the ground began rising again. Over approximately 2 years, it rose by 179 centimeters. The seismicity during this phase was severe. More than 16,000 earthquakes were recorded between 1982 and 1984, several of them strong enough to crack building facades and render structures uninhabitable. Approximately 40,000 residents of central Pozzuoli were temporarily evacuated. The Italian state spent significant resources on emergency housing and structural assessment across the municipality. In both cases, the uplift eventually slowed. The ground stabilized. People returned. The crises were declared over. The current phase has now produced more total uplift than either of those crises, and it has not stopped. It has been running for over 2 decades. Christopher Kilburn, professor of volcanology at University College London, has spent years analyzing how the rock beneath CAMPI FLEGREI responds to repeated cycles of pressure. In a 2017 paper published in Nature Communications, Kilburn and co-authors presented evidence for a progressive mechanical weakening of the crustal rock beneath the caldera. Each successive episode of unrest fractures rock that was already fractured. Each cycle leaves the crust less resistant to rupture than the one before it. The 1970 crisis did not fully heal before 1982 arrived, and 1982 did not fully heal before the current phase began in 2005. What this means in physical terms: the rock beneath the city carries the accumulated mechanical record of everything that came before. The ground rising today is not rising through intact geology. It is rising through a structure that decades of unrest have progressively weakened. And the instruments measuring that rise are recording something no previous generation had the tools to document in real time. What is driving the uplift, and what that question has not yet resolved, is where this record goes next. In the center of modern Pozzuoli, surrounded by a city of apartment blocks, bus routes, and fish markets, 3 marble columns still stand from a Roman structure built in the 2nd century of the Common Era. The structure was a macellum, a public marketplace. It served the ancient city of Puteoli, one of the busiest commercial ports in the Roman Mediterranean, the primary point of entry for grain arriving from Egypt. The columns are approximately 12 meters tall. They are intact, and approximately a third of the way up their shafts, at heights between roughly 3.5 and 6 meters above the current ground level, they carry marks that no stonecutter made. Those marks are the borings of Lithophaga, a marine bivalve that drills into submerged rock to create its shelter. The organism cannot survive above the waterline. It cannot survive in fresh water. It requires warm, shallow salt water, the kind found in the Bay of Pozzuoli. For those borings to exist at those heights on columns that were constructed on dry land, the ground beneath the structure had to sink far enough below sea level for marine water to cover the lower third of the columns, and stay there long enough for generations of the organism to drill, colonize, and establish layered communities within the stone. The ground then had to rise back up, carrying the columns and their biological record back above the waterline, where they remain today. This is not interpretation. It is the physical record, preserved in stone, of at least one complete cycle of major subsidence and subsequent uplift occurring after the Roman construction period, within the historical era, at a scale large enough to submerge a functioning public building beneath the sea. The Macellum di Serapide, named in earlier centuries after a statue of the Egyptian god Serapis found at the site, though the structure is now confirmed as a marketplace, became one of the most cited examples in geology precisely because it made the invisible visible. Charles Lyell, the Scottish geologist, whose 1830 work, Principles of Geology, laid foundational arguments for understanding gradual geological change, featured an engraving of the Pozzuoli columns as the frontispiece of his first volume. He used them to demonstrate that the ground was not static, that it rose and fell across centuries through forces that left permanent marks in stone. Nearly 2 centuries after Lyell's engraving, the columns still stand, and the ground beneath them is still moving. Giuseppe Orsi, volcanologist at the ENGV Osservatorio Vesuviano in Naples, has been among the researchers working to reconstruct the full cyclical history of the CAMPI FLEGREI system across geological and historical timescales. The Paleobradiceism record, the evidence of pre-instrumental uplift and subsidence cycles preserved in coastal sediments, archaeological structures, and biological markers, shows that what the 21st century is measuring with digital sensors and satellite interferometry is not a new behavior. It is the continuation of a pattern that the caldera has followed across multiple human generations. The columns do not predict what comes next. They do not need to. What they show is that the system completed this cycle before, sinking, flooding, then re-emerging, and left the record at heights that anyone standing in the square today can read with their eyes. The instruments on the sea floor and the GPS receivers bolted to buildings across Pozzuoli are measuring the same process in real time that Lithophaga recorded with its shell over 15 centuries ago. The difference is that the current phase has produced measurable uplift continuously for over 20 years, with seismic swarms intensifying in 2024 and 2025, and the ground that is rising now carries beneath it 2 decades of accumulated deformation that no previous monitoring network existed to document. What happened the last time Italian authorities had to respond to that accumulation, and what the response revealed about the gap between risk and readiness, is the record the next block reads. On the night of March 1, 1970, residents of the Rione Terra district of Pozzuoli were told to leave their homes. The ancient promontory, a limestone outcrop jutting into the Bay of Pozzuoli, inhabited continuously since at least the 6th century BCE, layered with Greek foundations, Roman construction, medieval churches, and Baroque facades, was being evacuated. The ground beneath it had been rising for months, generating enough seismic activity to threaten the structural integrity of buildings that in some cases had stood for centuries. The evacuation was presented as temporary. It was not. Approximately 500 families were relocated to a newly constructed residential district called Toiano, built on the slopes inland from the bay. They took what they could carry. Many returned to collect belongings over the following weeks. Some returned to find their apartments partially collapsed, facades cracked diagonally from foundation to roofline, staircases separated from walls. The Italian state sealed the Rione Terra promontory. Officially, the area was under evaluation for structural repair and eventual return. The return never came, not fully, not for those families. The Rione Terra remained a controlled archaeological and residential recovery project for decades, its streets silent long after the Bradiceism that triggered the evacuation had slowed and nominally ceased. The ground subsided. The crisis was declared over. The city moved on. In 1982, the ground began rising again. The second crisis was faster and in some respects more violent. Between 1982 and 1984, the CAMPI FLEGREI network recorded more than 16,000 earthquakes. The strongest reached magnitudes that cracked reinforced concrete, sheared utility lines, and rendered entire apartment blocks uninhabitable within days. The seismicity was not confined to the Rione Terra promontory. It spread across the municipality of Pozzuoli and reached districts that had been considered safe after the 1970 crisis. By October 1983, Italian civil protection authorities had ordered the temporary evacuation of approximately 40,000 residents from the historic center of Pozzuoli. Hotels in Naples and surrounding municipalities received displaced families. Emergency prefabricated housing was erected on available land. Schools relocated. Businesses closed. The city's population scattered across the wider Naples metropolitan area while authorities debated timelines and thresholds. The defining problem in both crises was not the absence of scientific monitoring. It was the absence of a threshold, a defined point at which the data would trigger a mandatory, irreversible decision. In 1970, the decision to evacuate Rione Terra came after the buildings were already compromised. In 1982-84, the decision to evacuate the city center came incrementally, neighborhood by neighborhood, as damage accumulated, with no single pre-established criterion governing when the trigger would be pulled. Researchers studying the social history of both crises have documented a consistent pattern. Official communications to residents were delayed, imprecise, or contradictory. Families were told to leave temporarily and then received no further guidance for months. Others were not told to leave at all, despite living adjacent to evacuated zones. The gap between what the instruments were recording and what residents were being told was wide enough that many people returned to their homes before authorities had formally declared it safe, not out of recklessness, but because no one had explained the criteria. The uplift from the 1982-84 crisis eventually slowed. The seismicity dropped. 40,000 people came back to a city that was structurally damaged but still standing. No eruption had occurred. The system had retreated, as it had in 1970, before crossing whatever threshold separates extended unrest from rupture. The critical question that both crises left unanswered was not scientific. It was institutional. If the ground rises again, rises further, rises longer, at what point does the decision become irreversible? Who makes it? And how much time does the science actually provide? That question has not been resolved. The uplift is still continuing. The geological record of CAMPI FLEGREI spans 40,000 years. The next part goes further back than either crisis, and deeper than any evacuation plan reaches. The instruments agree on what is happening at the surface. They do not agree on what is causing it. Beneath the CAMPI FLEGREI caldera, at depths that no drill has reached and no camera has seen, two distinct mechanisms are capable of producing the surface behavior that monitoring networks have been recording since 2005. The first is the movement of hydrothermal fluids, superheated water and gases circulating through fractured rock, expanding as they heat and pressurizing the system from within. The second is the accumulation of magma at shallow depth, fresh molten material intruding upward from deeper reservoirs, inflating the crust from below. Both mechanisms produce uplift. Both produce seismicity. Both leave signatures at the surface that, at current resolution, are difficult to fully separate. This distinction is not academic. It is the difference between a system being pushed toward a threshold it may not cross, and a system being loaded in a way that fundamentally changes what comes next. Giovanni Chiodini, volcanologist at the INGV in Rome, and one of the most cited researchers working on the CAMPI FLEGREI system, has spent decades studying the geochemical signatures of the caldera's fumarolic emissions, the gases venting at Solfatara, at Astroni, and along the coastal margins of the bay. His research group documented a progressive increase in CO2 flux from the hydrothermal system during the current unrest phase, alongside rising temperatures in shallow hydrothermal reservoirs. The data supported a model in which deep-sourced magmatic gases, primarily carbon dioxide, were infiltrating upward through permeable fracture networks into shallower hydrothermal reservoirs, heating the water, increasing pressure, and driving the surface deformation without requiring fresh magma to have moved significantly closer to the surface. In this model, the caldera is behaving like a pressure vessel. Heat and gas from depth are loading the system. The hydrothermal reservoir is the membrane under stress, and what fails first, if anything fails, is the rock separating the reservoir from the surface. The competing interpretation assigns a larger role to direct magmatic intrusion. Analysis of seismic velocity anomalies beneath the caldera has identified zones of partial melt and fluid saturation at depths consistent with a shallow magmatic body, material that, in some published models, sits within a few kilometers of the surface and whose behavior could shift if additional magma migrates upward from deeper reservoirs. In 2025, researchers affiliated with the GFZ German Research Center for Geosciences published findings identifying structural features consistent with fissure-like conduits at approximately 3.5 kilometers depth, geometries that could represent pathways connecting deeper gas and magma reservoirs to the shallow hydrothermal system feeding the surface fumaroles. The significance of this finding is not that it resolves the debate. It is that it maps, with greater spatial precision than earlier imaging allowed, the architecture through which whatever is happening at depth reaches the surface. A parallel study using a high-resolution seismic catalog compiled between 2022 and 2025 analyzed the spatial distribution and focal mechanisms of thousands of small earthquakes across the caldera. The results indicated that much of the seismicity during the current unrest phase is being controlled by fluid migration along pre-existing permeable structures, consistent with deep source degassing as the primary driver, but did not exclude the possibility of concurrent magmatic contributions at depth. What the science currently holds is this: the system is pressurized. The pressurization is real, sustained, and measurable. Its exact source, and the proportion of hydrothermal versus magmatic contribution, remains an open question that the available instruments cannot definitively close. Multiple research groups with access to the same monitoring data have published models that reach different conclusions about the likelihood and mechanism of a future rupture. This is not a failure of science. It is science working at the edge of what current technology can resolve in a system that has never fully erupted in the modern instrumental era. What it means in practical terms: the monitoring networks can detect changes. They can characterize trends. They cannot yet tell the difference, with certainty, between a system that is approaching a threshold and a system that will cycle back, as it did in 1970, as it did in 1984, without crossing one. The last time the threshold was crossed at CAMPI FLEGREI, it happened in 1538, and the record of what preceded that event is more readable than most people know. In the summer of 1538, the residents of Pozzuoli had been watching the ground for 36 years. The first reports of something unusual came from fishermen and coastal residents in the early 1500s, accounts that described new land appearing at the shoreline, sections of the seabed rising above the waterline in the shallow areas of the bay. By 1536, the pace of seismic activity had increased enough to register in contemporary written accounts. Churches were inspected for structural damage. Residents began relocating livestock and portable property away from the lowest-lying coastal areas. In the first days of September 1538, the seismicity intensified sharply. The ground shook repeatedly across the area west of Pozzuoli, in a flat plain between the bay and a chain of volcanic hills. Hot water and steam began venting from the ground in that zone, a low-lying coastal strip that held, among other things, the village of Tripergol, known for its thermal springs and bathhouses, which had drawn visitors from across the Kingdom of Naples for generations. On the night of September 27, 1538, the seismicity became continuous. By the morning of September 29th, the ground in the coastal plain west of Pozzuoli had opened. The eruption that followed lasted approximately 8 days. It was not a slow effusion, it was an explosive event, driven by the interaction of rising magma with the shallow hydrothermal system and groundwater. Ash, lapilli, and pyroclastic material were thrown into the air and fell across the surrounding countryside. By the time the most intense phase ended, a new volcanic cone had been constructed from the ejected material. It rose approximately 130 meters above the surrounding plain. The Italians named it Monte Nuovo, New Mountain. It still exists today, its crater accessible by trail, sitting less than 3 kilometers from the edge of modern Pozzuoli. Tripergole was buried. The thermal springs it had been built around were sealed beneath the cone. The settlement did not survive. Contemporary written accounts of the eruption exist in sufficient number to reconstruct the event's progression. Pietro Giacomo di Toledo, a Neapolitan nobleman who observed the eruption and its immediate aftermath, left a detailed description of the ashfall, the opening of the vent, and the behavior of people attempting to flee the coastal plain. A Florentine merchant named Francesco del Nero, resident in the area at the time, wrote an account that documented the days of seismic precursors immediately preceding the eruption and the visible changes in the shoreline, water retreating and then surging back, in the hours before the vent opened. These accounts, preserved in Italian archives and studied by historians of volcanology, form the primary eyewitness record of the only historical eruption of the CAMPI FLEGREI caldera. Several elements of that record are directly comparable to the current monitoring data. The precursors in 1538 included multi-year ground uplift beginning at least 3 decades before the eruption, progressive intensification of seismicity over months, then weeks, then days, thermal anomalies at the surface, hot water and steam venting from ground that had previously shown no such activity, and visible deformation of the coastline, with the sea floor rising above water level in shallow bay areas. In the final 72 hours before the eruption, the seismicity became effectively continuous. The monitoring network operating across CAMPI FLEGREI today records ground deformation, seismic swarms, soil temperature, gas flux, and changes in coastal bathymetry, precisely the categories of precursor that the 1538 record identified, observed with instruments of sensitivity and spatial coverage that no 16th century record could approach. The comparison is not a prediction, it is a structural observation. The system produced a set of observable precursors before its last eruption, and the categories of those precursors are the same categories that modern monitoring networks are designed to detect. What the 1538 record cannot answer is how much lead time those precursors provided in terms that translate directly to a modern evacuation timeline, because the 1538 eruption opened a new vent in an area that had not previously shown surface activity in living memory, and it did so within days of the seismicity becoming continuous. The question of what a future rupture would look like, where it would occur, how much warning would precede it, and what the population threshold for response actually is not answered by 1538 alone. It requires the deeper record, the one written not in eyewitness accounts, but in the rock itself. The The deeper record goes back 39,000 years. What happened then still matters for the 3 million people living above this system today. The caldera that exists beneath CAMPI FLEGREI today is not the product of what happened in 1538. It is not the product of the 1970 or 1984 Brady-sism crises. It is not the product of anything in the historical record. It is the product of an event that occurred approximately 39,000 years ago, an event so large that its physical signature has been found in sediment and ice cores from Scotland to the Caucasus, and its effects on the human populations of Europe at the time are still being actively researched. Geologists classify explosive volcanic eruptions on the Volcanic Explosivity Index, a logarithmic scale running from 0 to 8. The 1980 eruption of Mount St. Helens in Washington, an event that killed 57 people, flattened 600 square kilometers of forest, and reduced the mountain's summit by more than 400 meters, was a VEI 5. The 1991 eruption of Mount Pinatubo in the Philippines, which injected enough aerosols into the stratosphere to lower global average temperatures by approximately half a degree Celsius for 2 years, was a VEI 6. Each step on the index represents a tenfold increase in eruptive volume. The Campanian ignimbrite eruption was a VEI 7. Published estimates of the total volume of material ejected during that event range from approximately 180 to 300 cubic kilometers of magma equivalent, a range reflecting genuine uncertainty in the stratigraphic record, not imprecision in measurement. Even at the conservative end of that range, the eruption produced more than 100 times the output of Mount St. Helens. The material it ejected, pyroclastic flows, ash falls, and co-ignimbrite clouds carried on upper atmospheric winds, spread across an area extending from the Italian peninsula eastward across the Mediterranean, into what is now Turkey, the Levant, and the Caucasus region, and northward into Central and Eastern Europe. Identifiable Campanian ignimbrite ash layers have been found in marine sediment cores drilled from the Adriatic, the Aegean, the Black Sea, and beyond, a distributed physical record embedded in the seafloor at a depth that corresponds precisely to the stratigraphic layer dated to approximately 39,000 years before present. The caldera that formed when that volume of material was evacuated from the subsurface reservoir collapsed inward along its margins, creating the depression that Pozzuoli, Baia, Bacoli, and parts of the western Naples metropolitan area now occupy. That caldera measures roughly 12 kilometers by 15 kilometers. The Bay of Pozzuoli fills a significant portion of it. The city of Naples sits on its eastern rim. The Campanian ignimbrite eruption occurred at a moment in human prehistory that has attracted sustained scientific attention. Anatomically modern humans, Homo sapiens, had been expanding into Europe from Africa and the Levant for several thousand years when the eruption occurred. Neanderthals still occupied portions of the European continent. The potential relationship between the eruption and demographic changes in both populations in the millennia that followed has been studied by researchers at institutions including the Max Planck Institute for Evolutionary Anthropology in Leipzig, who have analyzed archaeological and genetic records from pre- and post-eruption layers across European sites. The evidence suggests that human populations in parts of southern and eastern Europe experienced significant disruption in the period following the Campanian ignimbrite event, though the precise causal relationship between the eruption and population change remains a subject of active research rather than established consensus. What the stratigraphic record does establish without ambiguity is the physical scale. The pyroclastic flows from a VEI-7 eruption at CAMPI FLEGREI would not stop at municipal boundaries or highway overpasses. They travel at speeds documented in historical and geological records as exceeding 100 kilometers per hour, carrying temperatures sufficient to incinerate organic material and collapse reinforced structures. The zone of total destruction in the Campanian Ignimbrite event extended across the entire Campanian plain. Beyond that zone, the ashfall was heavy enough to collapse roofs and contaminate water supplies across a radius of hundreds of kilometers. The Italian civil protection system does not plan for a VEI-7. No evacuation plan for any population on Earth currently addresses a VEI-7 event at this proximity. The planning framework for CAMPI FLEGREI is calibrated to the kind of eruption the geological record shows as more probable in a shorter time frame, a localized event more comparable in scale to 1538 than to the Campanian Ignimbrite. This is a rational calibration. It is also a calibration that requires acknowledging what it does not cover. The system that produced 39,000 years ago is the same system that produced 1538, the same system that is rising today. Italy has a national civil protection plan for CAMPI FLEGREI. It exists in published form, has been revised multiple times since its first version in the 1990s, and assigns specific responsibilities to municipal authorities, regional government, and the National Department of Civil Protection. The plan is real, detailed, and based on the best available scientific modeling. It also contains a structural assumption that the science cannot fully guarantee. The plan divides the territory around CAMPI FLEGREI into alert zones based on modeled hazard levels. The innermost zone, the Zona Rossa, or red zone, encompasses the municipalities most exposed to pyroclastic flows, ashfall, and ground deformation in the event of a significant eruption. Depending on the eruption scenario applied, the Zona Rossa covers a resident population of approximately 500,000 people. These are the individuals who, under the plan, would need to be evacuated before an eruption begins. The plan's evacuation trigger is tied to the National Alert Level System, which operates across 4 escalating thresholds: green, yellow, orange, and red. CAMPI FLEGREI has been at yellow alert, the second level, indicating ongoing unrest requiring enhanced monitoring, since 2012. An escalation to orange would initiate preparatory evacuation measures. Red would trigger the full evacuation of the Zona Rossa. The plan assumes that the escalation from orange to red would provide approximately 72 hours of lead time before conditions became unsurvivable in the zone. 72 hours is the window within which the road network, train capacity, and coordinated transport resources available to the Naples metropolitan area are estimated to be capable of moving 500,000 people out of the zone in an organized manner. The problem is, what 72 hours requires the monitoring network to deliver. For the civil protection system to escalate from yellow to orange to red with sufficient lead time for a 72-hour evacuation, the instruments monitoring the caldera would need to detect a clear, unambiguous, rapidly accelerating signal, a shift in the data that distinguishes the approach to eruption from the ongoing unrest that has characterized the system for over 20 years. The scientific community has not yet established a verified threshold that reliably makes that distinction. Christopher Kilburn's research on crustal weakening at CAMPI FLEGREI and parallel work by multiple INGV research groups has advanced the understanding of how the system behaves during escalating unrest. Tommaso Esposti Ongaro, a researcher at INGV who has worked extensively on the computational modeling of pyroclastic density currents, has contributed to published analyses of what a CAMPI FLEGREI eruption could produce in terms of flow velocity, reach, and thermal impact across the Campanian plain. That modeling defines what the evacuation is designed to avoid. It does not define when to start it. The 1538 eruption provides the only modern calibration point, and it is not reassuring in this context. The contemporary accounts document seismicity becoming continuous in the final 72 hours before the vent opened. If a comparable acceleration occurred today, and if monitoring networks correctly identified it as an eruption precursor rather than an extension of the chronic unrest, and if the alert escalation proceeded without institutional delay, the theoretical window would exist. But those three conditions operate in sequence, and each introduces its own uncertainty. There is also a physical infrastructure problem that the plan must work around. The road network connecting Pozzuoli and the western municipalities of the Naples metropolitan area to evacuation corridors runs through terrain that has itself been deformed by decades of Bradyseism. Several key roads pass through zones of maximum ground deformation. Some of the bridges and overpasses serving these routes were built or last substantially inspected during periods when the subsurface stress state beneath them was different from what the instruments now record. The plan does not ignore these constraints. It includes provisions for sea evacuation via the port of Pozzuoli and helicopter extraction for populations with mobility limitations. It has been stress-tested through tabletop exercises and, in 2019, through a partial field exercise called FLEGREI, which tested the coordination of municipal, regional, and national agencies across simulated alert escalation scenarios. What FLEGREI and similar exercises cannot fully replicate is the behavior of 500,000 people receiving simultaneous evacuation instructions while the ground is shaking beneath them. In a metropolitan area where the surrounding road network also serves the 3 million additional residents of Greater Naples who are not in the Zona Rossa, but who will respond to the same signals. The plan is the best available response to a problem that the science has not yet fully solved. That tension between a documented risk and an imperfect instrument for managing it is not unique to CAMPI FLEGREI, but it exists here at a scale and in a location that makes the gap between the two unusually consequential. The ground beneath that gap is still rising, and the record it is writing has been accumulating for longer than any plan addresses. The marble columns of the Macellum di Serapide are still standing in the center of Pozzuoli. On any given afternoon, they are surrounded by the ordinary activity of a functioning Italian city: cars navigating the one-way streets around the archaeological enclosure, a bar on the adjacent corner, pedestrians moving between the port and the commercial district that grew up around the old Roman grid. The columns rise above all of it, 12 meters of ancient stone, their lower third still marked by the borings of organisms that colonized them when this ground was below the sea. The monitoring station at Rione Terra recorded its data this week. The INGV bulletin for this month was published on schedule. The alert level remains yellow. The instruments are working. The data is flowing. And the uplift is continuing. What the full record of CAMPI FLEGREI shows, assembled from the biological markers on Roman columns, from eyewitness accounts of a 1538 eruption written by men who had no framework for what they were watching, from seismograms recording 16,000 earthquakes over 2 years in the 1980s, from GPS receivers and satellite interferometry tracking millimeter-scale deformation in near real time, is not a story that has a clear resolution. It is an open ledger. The entries in that ledger describe a system that operates across timescales that human institutional memory does not naturally encompass. A caldera that collapsed 39,000 years ago and has been intermittently restless ever since. A coastline that sank beneath the sea and rose back up within the span of a civilization that built a marketplace there and used it long enough for marine organisms to record the subsidence in stone. 2 episodes of modern unrest that forced tens of thousands of people to leave, both of which ended without eruption, and both of which ended without the underlying system having resolved whatever was driving the pressure. The current episode has lasted longer than either of those. The cumulative uplift has exceeded both. The seismicity in 2024 and 2025 renewed comparisons with the 1982-84 crisis, and the scientific debate about what is driving the current phase, hydrothermal pressurization, direct magmatic intrusion, or some proportion of both, has not reached a consensus that closes the question. What science has established is precise and important. The system is active. The crust beneath it is mechanically weaker than it was before the modern unrest cycles began. The monitoring network is the most capable ever deployed over this caldera, and the gap between what that network can detect and what it can forecast with the certainty required to trigger a 500,000-person evacuation remains real and unresolved. 3 million people live within or adjacent to the caldera. The city of Naples, 4 kilometers from the eastern rim, has a population larger than the entire country of Iceland. The port of Pozzuoli operates daily. The road network that serves as the primary evacuation corridor was built on ground that the Brachiocean has been deforming for decades. None of this means an eruption is imminent. The geological record does not support that claim, and making it would misrepresent what the science actually shows. What the geological record supports is more specific and in some ways more difficult to hold. The system has always continued. The intervals between its most significant events are measured in centuries and millennia. Intervals that are long relative to a human life, but short relative to the caldera's operational history. The borings in the Macellum columns represent one cycle. The Campanian ignimbrite represents another. The 1538 eruption represents another. The 1970 and 1984 crises represent others that ended without eruption, but not without consequence, and not without the system having moved. The ledger does not have a final entry. The instruments add to it every day. The columns in the square add to it across geological time, their stone carrying a record that will still be readable long after the monitoring network that surrounds them has been replaced several times over. What the ground beneath Pozzuoli is writing right now, in centimeters of uplift, in the frequency of small earthquakes, in the temperature of the fumarolic gases venting at Solfatara, is the current line in a document that began before any city existed here, and that will continue being written regardless of whether anyone is positioned to read it. The record has always been available. The question is whether the gap between what it says and what the institutions responsible for 3 million lives can act on has been closed enough.